Okay. So let me kind of go through all of these diagrams, because these are going to be like the most common that you're going to have. Okay. So on the first one, and this is like the classic quintessential one. That's why I started with this one, because this is like the easiest to draw. So there are certain things that you're going to have to make sure. I want to be able to clearly see, Vitor, bless his heart, even though we drew it extremely small.
Bless your heart, Vitor.
But I want to be able to see what's the object.
Oh, it's
Okay? All right? Now, you don't have to draw the carrot. You can draw a pyramid. You can draw a squirrel, a penguin, whatever. Okay? So, you have to keep track, because this plays out completely differently. Whether it's a convex lens or a convex mirror, they work completely differently.
Okay.
But what's common to both of those is the shape. So you see something like this, you know it's going to be a convex something. Fish?
So when you're drawing, like, you know how it's 10 centimeters? Is that from the middle, or is that from the edge?
Yeah, that's from like the middle. You treat that as like a point mass.
Okay, I was making sure it wasn't like...
Because that's where everything goes through, is through the middle. Okay?
I got it.
So you are actually going to set this up as a scale. You might say, you probably don't want to draw this thing out to 30 centimeters. So you might say, okay, like when I did mine, I let 5 centimeters equal 1 centimeter. That was the scale that I did. Okay? So when I actually drew this, like I made that distance 2 centimeters, okay? And then I made that distance 6 centimeters on my scale. Laid out, drawn, boom, here you go. So because of the fact that this is a convex lens, that light is going to originate here and go over. And it's funny how you get used to a mindset. Like if I would flip out, like if you made me put the lens over there and the carrot here, you just get into the mindset. I always draw mine from right to left. You don't have to. That's just what I always do. So when you have a lens, that light is going to try and go through that lens. So this is going to have 3 of them. So you're going to have a focal length over here at 10 centimeters. So you're going to have one, and you're actually going to draw this with a ruler. And you're going to have one that's going to go directly through the middle. Then you're going to have one that's going to go parallel with that axis. And then it's going to try and go through that focal length over there. And then you're going to have one that's going to go through this focal length, hit that lens, and go something like this. Okay? Now, that's a horrible drawing, because it didn't, but you get the idea. Now, so what's going to happen over here is that this is going to tell me a couple of things. First and foremost, that image is going to become inverted, okay? Because it's going to get flipped over. So this is what's happening in your eyeballs right now. You all have a convex lens in your eye. That's how it works. So everything that you see right now, you are actually seeing me upside down. Okay? The image that's on the back of your eye is upside down. Your brain flips it over, so it looks like right side up, but this is how a human eye works. So, now there's a couple of things that just, when you look at this, first off, what is that light as it goes through, is it being spread out or is it being brought together?
Brought together.
So start with this idea. As soon as you see that light is being brought together, whether it's a lens or a mirror, doesn't make any difference, okay? You don't have to think, oh, separate rules for mirrors, separate rules for lenses. No. As soon as you see that light being brought together, what's the sign of your focal length? Positive. So this is, my focal length is going to be some positive value, which in this case is going to be 10 centimeters. Now, It's a common misconception. Everybody says, oh, everybody tends to think, oh, the focal length is where the image is. No, 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 no. Focal length is not where the image is. The focal length is a property of that particular lens. Now, these are all made on the assumption that you are going from air into glass, something like that. And when you look at what's physically going to happen, these all have a certain index of refraction. And that's what's going to make this light bend. So because it's going from air into water, from air into this, whatever this is made of, that's what's going to allow it to bend. Now, if you look at this and you submerge this in water, water has like a bigger index of refraction. So if you put this into water where the indexes of refraction are smaller, that light won't get bent as much, and you actually would shift the focal length because of the fact that that light, if these were closer to the same index of refraction, that light wouldn't change as much, and your focal length would actually get farther away. Okay, but typically that's not going to happen unless you were specifically told something really strange. You assume that it's air and glass, Pyrex, whatever that is. Okay, so typically what you're going to solve for is the object distance. So, the image difference. So 1 over psi is going to equal 1 of your focal length minus 1 over, so your object distance is always positive, okay? You don't have to think about that. Object distance is always positive. So if you do this math, down there on the bottom half, on number 1, so you're going to take 1 over 10 minus 1 over 30, and then you're going to take the inverse of all of that, and you should get 15 centimeters. Okay? So hopefully that matches that diagram. So here's the spirit of how I want this assignment done. In the spirit of this assignment, you would actually do this diagram. You would do that first. You wouldn't even worry about the thin lens equation. You would do that diagram first, and you would measure this distance from that lens out to where that image is. Okay? Now, I'm going to be real suspicious if every one of your distances that you theoretically measured is the exact same as the calculated value. Okay? That wasn't the point. Okay? The point was that you use your diagrams to get those distances. Then you calculate it to compare it.
That is tough.
Oh, I thought it was calculate and then do it.
No, that's why I had you do that first. If I wanted you to calculate it first, I would have had you do the calculations first.
Sold the bag.
So, don't worry about it, really. It's not that big deal.
It's okay, I didn't get far enough.
It's a huge deal.
I did that on all of them.
So, what I want is your image distance. Tell me, is it upright or inverted? And then the magnification. So, your magnification, and there's a couple of different ways you can do the magnification. You can look at it as a ratio of your object and image distances or the ratio of your heights, okay? In this situation, you don't know the heights, so I would just work off of the psi and the so. What you should get is a negative magnification, which means that that is an inverted image. So anytime you see a negative magnification, that's an inverted image. Now,
Grab them.
Okay. Okay. Now, let's talk about the sign of your image distance. Your object distance will always be positive. Your focal length can be positive or negative depending upon whether it converges or diverges. In terms of your image distance, and this will make sense, if your image is in the same direction the light is traveling, you're going to have a positive value for your SI. And that's what's happening here. So the light is going in this direction, and that's the same place that your object or the image is being formed. So the light's going this way, the image is there, boom, you've got it. This would also, and we'll get more into this, but this would also be a real image because you could project that onto a screen. Now, when you get to number 2, you have a diverging, on number 2, you have a diverging lens with a focal length of 10 centimeters. So with this one, diverging lens is the same thing as a concave or convex lens. It's a so this is concave, but this is a lens. Okay? So what this means is that when this light hits it, it spreads out. Okay? So as soon as you see that that light's going to spread out as a lens, what's the sign of your focal length?
Negative.
Negative. Now, if this had been a concave mirror, then that light would become more focused and the focal length would be a positive value. But since this is a concave lens, not a mirror, the light gets spread out. Now, this is one of, hold on.
Wait, so if it's concave mirror, it's going to be positive?
On the focal length. But a concave lens, the focal length is negative. So with this one, so you've got a focal length here, and then you have your object.
This is the candle question, correct?
Yeah, this is number 2.
Okay. I need to pay attention.
For your focal length is like 10 centimeters, your object distance is, so this is the one with the candle, right? Doesn't matter. What?
How do you know if the focal length is negative or positive?
What, it's just whether the light gets converged or diverged.
I don't want to talk about what do you think?
No, what? This is a Connor thing. You have a sword?
I would have a sword. I just bought it from Quick Shop.
Who did a sword?
No, I wish I could keep my
Who
sword
doesn't
that
want
I
a sword,
made.
Mr. Burkham?
I made it welding. I made this sword,
Was it
but
nice?
this garden didn't let me take it home.
Why?
If it was violent?
How are you allowed to make it but not take it home?
I had to destroy it after I made it.
What?
Wait. I had to like cut it with the
What kind of
plastic cutter.
sword?
A metal one.
No, but like, was it a child?
Hence welding.
No, bro, it was
Yeah, it was
I just told him
It was like this big.
How'd you make it in the first place?
I got 2 long pieces of metal. I welded them together, then plasma cut out a like sword design.
You didn't do like a Damascus steel or anything.
No, no.
Make a
Connor
door.
will do Damascus steel?
I'm
Huh?
not him.
Look at his hand.
What?
No shot.
I'm not that
He's
gifted.
saying.
I just like
Louis on his
I like making ninja stars too. Those are fun.
Okay.
It's like Batman.
This teacher
All right.
just walk in and drink
So, let's talk concave lenses, okay? Now, we'll actually see this image tomorrow when we do the lens lab. So with this one, this is a situation where the light is being emitted from here. It's going through the lens, but part of that energy, part of those photons are refracted back in the opposite direction. So what you would see, this is going to look like a mirage, okay? Like it's going to look like it's like a hologram, okay? This isn't something we could project onto a screen. So when you have a concave lens, that light is going to hit this lens and it's going to try to spread out, okay? So as soon as you see that that light is going to try and spread out, then that focal length, when you do this calculation of 1 over your focal length minus 1 over so, this is now going to be a negative value. So it's going to be the inverse of negative 10 minus 1 over 20. Remember, your object distance is always a positive value. This is never going to be negative, okay? So when you do this, you get negative 0.66.67 centimeters, which should match with this diagram. So here's your focal length. Your candle is showing up inside of that focal length. Okay, so this is inside that focal length. So this calculated value of my image distance is inside that focal length.
How come you only have 2 rays on this one?
Well, I just hadn't drawn the third one yet.
Can you draw the third one?
Hold on, let me get done with math, okay? So, the first one, well, let's talk about, we're talking about rays. So the first one's gonna come in, it's gonna hit, but what it's gonna try and do is go back through that focal point, okay? So it's gonna hit, boom, so you just can't randomly draw it scattering. So what's gonna happen is that's gonna try and come back and hit that focal point. So as soon as you do that, I know that that candle is going to be somewhere in this triangle. Okay? As soon as I get that, I know it's got to be somewhere in there. Now, what the second one's going to try and do is it's going to try and go completely through here to this focal point on the opposite side. But it's going to hit, and then it's going to go back parallel with this. So right now I have 2 of my rays that are telling me, hey, this is where this is going to be. Ideally, you have 3, because what the third one does is just confirms what the other 2 already are showing you. So the third one is just like a confirmatory ray to detect that. Now, let's talk about the sign of that image distance. So notice on this one has a negative value for the image distance. What that tells me is that this is in the opposite direction that the light is going. So the light is traveling in this direction, but the image is over here, okay? And that's in the opposite direction the light is going because some of that energy is being refracted back. And so what this would look like is a faint image, and it's going to look like a mirage, okay? This isn't something that I can project onto a screen, okay? Now, let's talk magnification. Magnification, and here's the significance of that negative sign. So, your magnification is negative psi over so. So right now, just based upon this diagram, I know a couple of things. My magnification better work out to be a positive value because it's upright, and my magnification better be less than 1 because what I'm doing is I'm producing a small upright virtual image. And that's what's going to happen right there. So that would appear as like a tiny little floating candle. And this is one of the toughest ones to actually make happen because the optics have to be just right. It has to be really dark, and it's that one. So tomorrow when we do this one, this is the hardest one to see because it's going to appear as this floating little mirage, and if you don't look in just the right spot, you can't even see it. Sam?
Can you go over again how you know when there's like light reflected back from the
Okay.
lens?
So part of it is just knowledge. Okay, hey, I know on a concave lens, okay, that the only thing that can happen with a concave lens is that I can produce a virtual image. So if you just go with that knowledge, okay?
So if it's concave, it's virtual no matter what.
No. On a concave lens,
On a concave lens.
yes.
Okay.
On a concave lens, not a concave mirror,
Okay.
on a concave lens,
Okay.
there's only one option.
Yeah.
One
virtual.
option only. You're going to make an upright virtual image.
Okay.
That's it. And the only way that can happen is if that's going to hit this lens, and then it's going to, part of that's going to get refracted back. Because here's the deal. This is why you can't see anything on this side, is because of the fact that that light is getting spread out. Okay?
Okay.
So, let me see. I should have. Give me 1 second.
And then when you graph that, it's still the same thing where it goes back and do your focal length.
Hold on.
Are you looking for it?
I had. You know, what's that?
You need a ruler?
What does that say?
Double convex.
Hold on. Give me 1 second.
Chill out, be still honest. Buddy, I am drawing.
Third one.
Yeah, it should be
But it
like.
looks like that, like the big one.
Be careful.
So that's better.
It's gonna
He's like out of breath.
Okay, so here you've got, this, I'll pass this around. So this is a double concave lens, okay? So this is going to be like this. So if you hold this out, there's a couple of things. As you're seeing this light, as it's coming through and you're on this side, okay? If I hold this up, you all look really far away, okay? And you look small, because what's happening as that light is passing from you guys to here, what's happening is that light is diverging out. So the actual image that this is producing would be on this side. So if you guys are like the object distance, you guys are well out there. So when I look around, what's happening is that, number one, I'm seeing images that are upright. This doesn't flip it over if I'm on this side of it. Because what's happening is that as that light comes through, it's like a scatter shot. It's going to spread out like this. So this is what you might see like in a mirror, in a door. So you might put a concave lens in a door, because it's not going to flip it over. So imagine that you're looking through your door and you're seeing something that's on the other side. So if I hold this up, and this will make sense when you look at it, like right now, Gracie looks really far away. She looks really small, because that light coming through here is hitting this, and the reason that she's not getting flipped over is because that light is going like this. So the only way you can flip an image over is if the rays are going to cross. And this is why when I look, and if you bring this close, you get a completely different perspective than if you're at arm's length. So, pass that around. So hold it up close and then move it far away. Okay. Okay.
Still,
Okay.
And you still on top, and you go. And pay for that pop?
Yeah, it goes to this one. Hey, my dude. And then the last one is just here.
Okay, so Louis, you asked for the three diagrams.
Yes, please.
So one goes parallel, hits this, and then it tries to go back through this focal length.
Yeah.
The second one is gonna try and go from that point straight through this focal point on the other side, but it's gonna hit the middle and then it's gonna go back parallel with that optical axis.
Oh, it goes back parallel?
Yes, parallel with this, so it's gonna go straight through to here, it's gonna hit this, and then it's gonna go straight back. And the third one is gonna go from this candle right through the middle bottom of that ray diagram.
Oh, okay, so you have two reflections and one real?
Yeah, well, this one actually is gonna hit this, and it's just gonna go back on its own path.
Oh, I get it.
That's the only one that goes back on its own path.
I knew I should have guessed. That's the worst thing I've ever seen.
Okay, that's one of the harder ones to draw. What?
How close are you? One.
Well, as long as you're relatively close, I mean,
Okay, I just said 6.25 something.
the main thing is, here's what I'm gonna look for, fish.
Yep.
Can I clearly see where the object is? Can I clearly see where the image is? Can I clearly see where the focal points are?
Yeah.
And is it relatively close to what it should be? So like if you draw this, and the focal point's here, and you have the image out here, that's a train wreck. So like here, as long as that image is between that focal length and that mirror and closer to that focal length, I'm good with it. Okay? But if you have it over here, that's bad. If you have it over here and inverted, that's even worse.
Yeah.
Okay?
Okay. I'm good.
Okay, I was asking for a friend.
I had -7, so
Okay.
I'm not too far.
Now,
Yeah.
let's talk about number 3. So when you have a concave mirror, and this is what you're going to do in the lab today. Today's lab is going to be on mirrors. So when you have a concave mirror, it can produce two different images depending upon where you are relative to the focal length. But no matter what, when you have a concave mirror, no matter where you are, the focal length is always going to be a positive number because it's always going to take that light and try and focus it back together. So if you're ever out in the desert, hypothetically, and you have a mirror and you're going to try and start like a fire, take a concave mirror and that will allow you to take that sunlight and focus it to a point. Okay? Don't try and do it with a convex mirror. You're not going to get anywhere because it's just going to reflect it off and scatter it.
There's a high possibility that probably happens to me in the future.
Well, don't. So, but I'm just telling you, if you were ever need to start a fire and you have a concave mirror, you can do that, but you've got to find the focal length. And I'll show you that on a large scale tomorrow because I do it today, but it's just really, really cold outside. Okay.
What are glasses convex then?
It depends upon what if you're nearsighted or farsighted.
Because some glasses they can like do that too.
Yes.
But it's a lens, so it has to be a convex lens.
Yes.
Right?
Yes. Okay. So, on number 3, so here's your concave mirror. Now think about this. It's a cosmetic mirror. You want your image to be upright or inverted?
Upright.
Upright.
Inverted.
What do you want the magnification to be? Less than 1 or more than 1? More than 1. You want to see an upright image that's big. That's it. Okay, start with that idea. Now, so if you go through this one, you've got this one, you have a really, really, really long focal length out here at 40 centimeters. And the object distance is here at 20 centimeters. And here's your brush. Okay? Now, this is what I always do when I draw, this is just what works best for me. Regardless of what type of mirror it is, here's the first thing I do. Like for example, let's say on this one, I'm going to count up from this central axis 1, 2, 3, 4. 4 grids. I'm going to come down here and I'm going to count 1, 2, 3, 4. Okay? So, let me get rid of this. So, I counted up 4, and then I'm going to come down 4, and I'm going to make a mark. So the first thing I'm going to do is that I'm going to draw a symmetrical angle. I'm going to draw it from here to the center axis of that mirror, and then I'm going to bring that out like this, and then I'm going to extend that out. Okay? So here's the importance of this. Right away, this tells me one of two things. That image is either going to be here or it's going to be there. That's the only two options that I have. Okay, that's why I drew this. So if it's here, obviously it's going to be inverted. If it's out there, then it's going to be right side up. So this is why, this is the first thing I drew with mirrors. I don't care where it is. And I don't care what your scale is. You figure out where that object is. You flip that over. You draw a symmetrical line. So this angle here is the same as this angle here, which means it's going to be here or it's going to be there. And that works whether it's a convex lens, concave, concave mirror, convex mirror, doesn't make any difference. It's the first step that you do. Then, when you get that drawn, then you can start your other ones. Now, so I'm going to draw one parallel with this line, and it's going to hit this, and then it's going to try and go back through that focal point. Now, this is why you actually draw this with rulers and not try and freehand it. So, here's what I've got. So, you got to look at this from two different perspectives. Right away, I know if this is a concave mirror, this is just general knowledge that you have to have. Oh, I'm inside the focal length. I'm going to have a big upright image. It's a cosmetic mirror. The only way that can happen is if this image is somewhere over here. And the only way that can happen to get big is if this value here, this image here, is bigger than what I started with. So what this has done, I took this line and I drew it parallel with that axis, and then I sent it back along, and it's trying to go through that focal length. But then if I extend it back, it's going to go in that opposite direction. So right now I have two lines that are going to meet and go, wow, okay, it's kind of cool. This is where I'm thinking that's going to go. So, but here's physically what's happening that's allowing you to see this. Your eyeball is here, okay? Your eyeball is here. So what's happening is that your eyeball is here, and these rays are bouncing off this mirror, and they're hitting your eye. Your eye is trying to work backwards and go, what am I seeing now? It's kind of cool. What am I seeing? So your eyeball is collecting these rays after it bounces off the mirror. So when you look at it, your eye is going to say, right. I got a right side up image that's big because your eyeball can't tell the difference. Your eye can't tell the difference if there's a paintbrush out there emitting light and that's what you're seeing, or your eyeball can't tell if it's light that's reflected off this mirror hitting your eye, because your eyeball is always going to try and trace backwards to where it is. Okay? So your eyeball is going to look and go, oh, right, I see a paintbrush on the other side of this. But because it's over there, this is a virtual image. There's no way I can project this onto a screen because that light is hitting and it's going to come this way, but your eye is going to try and transpose it and work back to here. Okay? So that's situation number one. With that concave mirror, in this situation, your object is inside your focal length. You get an image that is upright and magnified. Okay? That's why we use those in cosmetic mirrors. Now, in contrast to that, on number 4, and this is why I sequenced these like I did. On number 4, you got a light bulb 60 centimeters away from a concave mirror with a focal length of 20 centimeters. Now, so what's happening on the next one, when you get to number 4, again, it's concave mirror, right? But with this one, you have a focal length of 20 centimeters and an object distance of 60 centimeters. So here's the light bulb. Okay, and again, this is what I would do. Whatever scale that is, whatever this distance is here, that's whatever distance is I'm going to have down here. I'm going to draw this like this and extend that back. So here's what I know, is that it's either going to be here or it's going to be there. Those are my two options. Okay? It's either going to be here and inverted or there and upright. Okay? That's it. Those are my two options. So, if you come in here and you draw that third one, come in here, draw that parallel, boom, it's going to hit that focal length, and it's going to go down something like, and this is as crude as drawing as you're going to get. So, what's going to happen here is that this image is going to appear right there. So right away, I know a couple of things. I have an inverted image, and I have a magnification that's going to be less than 1. So this is why, if you take those little mirrors, and they're up close and you look at it, you see yourself big. You take it away and you move outside that focal length, you'll see your image flip over. Now, this one, though, is something that I can project onto a screen. So today is mirrors. Okay? This is going to be one of those that you're going to do. You're going to take a mirror, and it's going to be a concave mirror, and you're going to look at that inside of that focal length. And you're going to see an inverted image that's real that you can project onto a screen. Okay. Now, the last kicker. On number 5, you have a convex mirror. Central, primary, boom, wherever you're going to put your object. What is this? A bicycle. Okay, so here's your bicycle. Focal length is 2 meters, and you're 4 meters away. Again, here's what I would do. Come in here and draw these symmetrical lines, which is going to put me somewhere back over here. Now, convex mirrors only produce virtual images, okay? And here's the reason why. The optics are that it's going to hit this mirror and it's going to scatter, okay? Since that light is scattering and being bounced off of here, there's no way that I can make them cross on this side because it's hitting here and they're being spread out, okay? So right away, I know that that image has to be somewhere on that back side, okay? I know that's where it has to be. Anytime you have a convex mirror, there's no thinking, oh, the image is always going to appear on the back side of that. That's it. Always going to happen. So when you do this diagram, you get that, and then you draw one parallel with it, and then it's going to try and go through that focal length. No, it's going to go through the focal length on the other side. and there's gonna be your upright motorcycle. So this is why, if you look on your rear view mirror, I don't know if they have them anymore, but that was always the rage. They would say objects in mirror are closer than they appear. And here's the reason why, is that if all you saw was that small little bicycle looking in the mirror, and you can't see anything else, and that's all you saw, you would think, wow, that bicycle is a long way away, because he's going to appear small. And you would think, oh, okay, that's a long way away. Okay, in reality, they're much closer. So does anybody have that in their side view mirror? Do you?
Yeah.
That's the reason why. That's also why we use convex mirrors and not concave mirrors, because if you have concave mirrors on rear view, it might flip over. It's like, whoa, that got really close and it flips out. Okay, it's like, whoa. Okay, that's why I use convex mirrors, because you never have to worry about that image being flipped over. Aspen?
Why don't they just use a totally flat mirror?
Because the advantage of convex mirrors is because it scatters that light out, you can actually see more because that light is being diverged out. So that's why. You can actually see a little bit broader area of view. Okay? On that back side, on the ones on 1 through 5 where they're doing those pure calculations, so let me just give you some ranges on what your image distances should be. Okay? So on number 1, that image distance should be around 40. On number 2, and I'm not telling you positive or negative, I'm just telling you the numeric values.
Wait, is this for the?
This is on the back side,
Okay.
where you're just doing the pure calculations. So the first one's around 40. The second one's around 10-ish. Okay? The third one, and these are your image distances. The third one is also around 10. Your fourth one is around 40. And your fifth one is around 60. Okay? Now, those are ishes, and I'm not telling, some of those answers are positive, some of them are negative. Okay? So, when you get done, here's what I want. Staple the diagrams to the back. Make sure that you have labeled the image, the object, the focal length, okay? And then also on these where you're just, making these sketches, again, make sure that I at least know what the object in the image is, okay? So help me. If I can't tell that, I'm not even going to look at it.
What did you
Fish?
say for 3, 4?
Huh?
3 and 4?
3,
Yeah.
the image distance is around 10,
Yeah. 4.
and on 4, that's around 40.
Thank you, Fed.
Got it? Anything else?
You said you want to go look at it if what?
If I cannot clearly look and see what the object and what the image distance is on these sketches on the back, I'm not even going to grade it.
Just put 100 then?
Especially just for you, Fish.
Thank you, I appreciate that.
Automatic 100.
You should
Boom.
just do that for everything.
Yeah.
I should.
Pass anything.
Yeah. Oh, Fish, 100%. Boom. Here we go. Okay. Anything else? Going once, going twice, sold? Okay. Get that handed in.
Like there's a fire at your house and someone saves you, they get 100 for the rest of the year.
Why would they be close to his?
Yeah, right away. That's a little. I just happened to be driving Brookham's house by his house when the fire started. What are the odds?
Has a gas tank and like a
And a concave mirror. Like, what were you doing? Just a little experiment,
Don't worry about it. Testing the flammability.
Am I 100% or not?
Testing the flammability of the house.
Or better than the flammability of the physical, which we'll talk about tomorrow when we do the advanced demonstration.
That's flammability of a physics teacher. We're gonna talk about that.
Specifically of the pants that I'm wearing. So it'll make sense tomorrow when I read everything else.
We're gonna catch it.
If we have to do any more of those drawings,
Yep.
do you really think we weren't going to? I thought maybe this was enough of it.
No, one and done.
Oh, no.
Oh, I see 2 more. I see 3 more.
What?
They're literally easily super
Who's gonna say it? I can't look up the issues.
What is you actually? I don't think it does, but if you actually.
Yes, sure.
I know it's pretty funny. Just think about it. How do you know how to do it?
Oh my god. What happened?
Mr. Burkett,
What?
Who did that?
on number 3, you never did the third line, and
He's bamboozled.
I'm still confused. Like, 'cause
Yeah, I can help you.
the lines of imaginary.
Maybe you see if F is.
Okay,
Dotted.
For which one? Which line do you have?
This one.
so let's go to the back and I'll kind of show you what's gonna happen.
That's the thing.
I didn't actually stop this.
I could sabotage Morella.
So wherever your Pokemon is on. Let's go.
Start here. Okay. So let me explain how these next 3 days are going to play out. So today we're going to start on this lab, which is going to be on mirrors. Tomorrow we're going to have a lab on lenses, and then this never happens, but this kind of gives you an idea of how much time this is going to take. So today's lab on mirrors. Tomorrow, lab on lenses. Quit kicking that balloon before I kick your head. Thursday is just going to be a work day. Okay? That's it. So next 3 days, you have basically 3 days to do 2 labs. Okay? So basically today I'm going to get you started on the mirror. Tomorrow I'll get you started on lenses, and then everything is going to be due hopefully by the end of the day on Thursday. Okay? That's kind of the big sequence. All right. So what I want you to do first is basically do a little bit of investigation. You're going to take the concave mirror, okay? And if you're not sure which one that is, this is how you can tell. At arm's length, so this is going to be the concave mirror. You're going to hold it out like this. You're going to bring it close. You're going to take it further away. And you're just going to see what's going to happen with that, okay? And then you're going to make some observations. And then the convex mirror, which is going to be like this one over here, then you're going to do the same thing. Take that convex mirror, hold it at arm's length, bring it closer, tell me what you see. Then you got some questions to answer about that. What's the sign of the magnification, if it's positive or negative in terms of it's upright or virtual? Now, when you get to this one, this page 2, so what you're going to do is I'm going to give you the object distance. So this is going to start here at 10. Okay? Then you're going to put this out here at 110. So that way you have a distance of 100 between the two. And then what you're going to do is that you're going to adjust this mirror, and this is why this can pivot. And you're going to move this in so that that 4 gets into focus. So what you want to do is that you're going to record the image distance, which is going to be the distance from here to here. So you know where this is, you know what this is, do some subtraction, boom, there you go. Now, the focal length is what you're going to calculate, okay? You don't know the focal length. That's one of the things you're going to determine. You're going to measure the object height and the image height, okay? So the object height is going to be this. That's going to stay the same throughout the entire experiment on this particular one. So you need to measure this. Use the precision of the centimeters. Like, can you go to the tenths? Can you go to the hundredths? Now, the tricky part is measuring the image height, because you've got to try and measure the image of that 4 when it's in focus. So what you want to do is take that out past, bring it back so it's in focus, and then just kind of adjust that so that you get the clearest possible 4 that you can. Okay? Now, the tricky part is measuring the height of that 4. What some people will do, they'll take like a little piece of paper and they'll hold it up like this, and then they'll make like a mark. They'll take their pencil and they'll make a little mark on the piece of paper, and then they'll take that out and they'll measure it. That's about as easy. You can take your ruler and try and measure that, but the problem is that that's recessed in this frame, and you're trying to measure that height. That gets a little sketchy to try and do. But the quality of this lab is going to come down to how good your data is. Now, the next thing that you're going to do, you're going to change things. So you're going to get all of that data. You're going to calculate your magnification. Obviously, looking at this, you have a really small 4. So your magnification should be less than 1. Okay. So then you're going to set it to 90. So you're going to bring this 10 centimeters closer. Okay? And then you're going to do the same thing. Then you're going to figure out where that is. And you want to look at it from this side. And you want to get that as clear as focus as you can. Again, this image hasn't changed, but that image height has. And then you're just going to keep going closer and closer and closer. Now, what you should see is that the 4 is getting bigger and bigger and bigger. Okay? So the image height is really small when you're out there, but the closer this gets, then you go like here, then notice this one is bigger and bigger and bigger. So as this shrinks, this is getting bigger and bigger and bigger. So and you don't have to show me every calculation, but at least show me one good set of calculations that says, here's my calculation of my focal length, here's my object height. Those are just things that you're going to measure, and then your magnification. So there's 2 calculations that you have to do: your focal length and your magnification. So then, this is just for you, Pop. Over here on number 4, okay, then I'm going to ask you some questions, right? Happens to the size of the image. Is the image flipped on the x-axis? Okay. In other words, like, here's your x-axis. Is it flipped this way? And then is it flipped on the y-axis? Okay. Is it flipped this way? Those are just yes/no questions. So down here on number 5, in the space below, choose a suitable scale. Show me what the scale is. For a ray diagram for the 80 centimeter distance, you have to draw the 3 primary rays and label the focal points and obviously the image and the object. Explain the sign of the magnification, remove the half screen, and then you're going to do another set and move that to the slowly slide the mirror. Okay, what's going to happen to that image? Okay, so this is going to be another set. There's no real calculations to do on this, but this is just asking us the questions. Is it real? Is it virtual? What's the sign of your focal length? Is that positive or is that negative? All right, now, the next part with the convex mirror. This is the hardest thing I will ever, from my perspective, that I have to teach you. Because I can't show you, I can just explain what's going to happen. So this is going to be this setup over here. So this is going to go off this thing called parallax. So here's the simplest way to look at parallax. So if you hold your thumb out in front of you and you close like your left eye. And don't move your thumb, okay? Just close your left eye and look at it. Now, close your right eye and then look at it through your left eye and go back and forth. What does the thumb appear to do? Move. Now, bring it closer and do the same thing.
Nothing. It still moves.
It still moves. When does it move more? When it's further out
Further out.
or when it's closer?
Closer.
Moves. Now, this is actually what we do. We use that as an estimate of distance to stars. Imagine that the Earth is orbiting around the sun. Imagine that you're on one side of the Earth, on its orbit, and you're looking at a star. Come over here 6 months later, you're on the other side of the orbit, and you're looking at that same star. So what's going to happen is that star is going to appear to shift. And the farther away that star is, guess what? The less it shifts. The closer it is, the more it shifts. So that allows us to get an estimation of how far away stars are based upon that parallax shift. So you got the idea of what parallax is.
Yeah.
Now, here's the problem with convex mirrors. I can't project it onto here because it only produces virtual images. So I can't measure heights, I can't measure distances, I can't do anything. So what we're going to do is we're going to take advantage of this deal called parallax. So here's what you're going to do. Watch out. So what you're going to do, like I said, of all the things that I ever tried to teach you the entire year, this is the hardest thing because I can't show you what it looks like. But I can explain the technique. So what you're going to do is you're going to start with realizing that this is a convex mirror. So you need to get down, and what you're going to do is you're going to look and you're going to see the convex mirror here. So that light is bouncing off of that, and it's coming back towards you, and that light is getting spread out. So what you're seeing, when I look through here, if I didn't know better, I would look through here and think, oh, there's a piece of glass, and I'm seeing me on the other side of that. But I'm seeing me smaller because it's a convex mirror. So what you're going to do, and like I said, this is tough to explain. And you can read through the lab, and I'll try and do it as best I can. But what you want to do is you want to eyeball and look through here, and you're going to see the image of the mirror, and then you're going to see an index card with a line up there. So when you move left or right, what you'll see is that this image moves relative to the line on that screen. Okay? We can't measure this distance directly. We can't produce an image. We can't do any of that. So we have to use this concept of parallax. So you're going to start, and if you start pretty close, this becomes pretty obvious. So when you shift it, what you'll see is that this image that you're seeing in the mirror is moving relative to that vertical line that's on the card. So then you can get an idea of what that's going to look like. Then you're going to move it back about 5 centimeters. Now, when you move it back about 5 centimeters, what you should see is that that amount of shift becomes less because it's further away. And what's going to happen is that, and like I said, this is tough to do, but if you go far enough, way back, then when you do that shift, it actually goes in the opposite direction. Because now, instead of moving like left to right, it'll move right to left relative to that screen. So what you want to do is, oh, that didn't work well, is find the point where when you do this shift, that it doesn't really move at all. That's the distance that you're looking at, okay? It's a heavy sigh, okay? It's a heavy sigh because even as many times as I've done this, I kind of know what to look for, but I can't really explain it. But I'll tell you this. So you have some idea. That distance should be between like 12 and 16 centimeters. Okay? So when you get that distance, it should be between 12 and 16. So if you're at 20, you blew right through it. It's going to be, and if you're at 10, too close. It's going to be somewhere between 12 and 16 centimeters. Okay? Like I said, this is the most frustrating thing for me as a teacher because I can describe it, but I can't show you because it's something that you have to see. All right? Okay.
Should we look at it real quick?
Yeah, you can look at it, but all right. So I am done. So you have the rest of the day to work on this. So what's going to happen tomorrow is that I'm going to introduce the lens lab, and then you're going to have, you got the rest of the day, all tomorrow and Thursday to do the two labs. Okay? Ready to break.